As usual, I forget to start recording. Thomas Milling is there to back me up, but so I just started now. So we're live on YouTube and we're recording. A few months ago, I was still hoping that we're going to do this live in Vienna. And if you were in Vienna today, you would be not disappointed. We have a mild -6 degrees today, which compared to a meeting we had in Krakow a few years back with -25 is really a summer temperatures. So I don't think I have to present you Harvey Reall, that everyone knows him. He's a professor at relatively young Cambridge University. I will not present his title because he's going to present it to us. We still have 3 minutes to go. So if somebody wants to fill in the 3 minutes with some comments before unmuting yourselves, no, nobody wants to comment. Well, so let me just say that I'm really happy that this Central European Relativity Seminars survived 11 years now, and each year we're wondering whether we want to do this again or not, but the number of people that are interested makes it clear that there is some interest. So let's hope it's a useful service to the community, and we're always very happy to hear talks from graduate students, recent postdocs who are just bringing new ideas to the field. So given that, still 2 minutes to go. Yeah, so I can tell you my mild comic joke, which is a guy which is stopped by a policeman and who says, "Mister, you have been drinking," and the driver says, "Well, it is because you're not respecting social distancing." Anyway, I think Harvey, maybe you can start your screen.
Okay. How do you want to handle questions? Are people just going to interrupt if they have questions, or are you using the chat?
Well, so is it okay with you if people ask questions?
It's fine with me, but if they do it using the chat, I might not notice. Well, I definitely won't.
Well, yeah, so Thomas will be there just to monitor this.
Okay.
So, those of you who were with us last year in Gaume, and that was these funny times where you could have real life meetings, might remember a talk by Stefan Hollands about similar topics. So we will have a fresh perspective on the recent developments in strong cosmic censorship by Harvey Reall. Harvey, the screen is yours.
Okay, well, thank you very much. It's always a pleasure to visit Vienna, if only virtually. So I'll be giving an overview of some recent developments in strong cosmic censorship. So in this talk, the first half or so of the talk is essentially going to be a review of the current status of strong cosmic censorship, and then I'll move on to describe the more recent work that I've been involved with, which is contained in the papers listed here. The ones in bold are the ones which I would recommend you take a look at if you're interested in learning more, because these have fairly pedagogical introductions. So the outline of my talk is I'll start by describing the situation with strong cosmic censorship for vanishing cosmological constant. And then I'll come on to the newer stuff, which is some violations of strong cosmic censorship with a non-zero cosmological constant. And then at the end, I will discuss some ways of rescuing the strong cosmic censorship conjecture from these violations. So let's start with 0 lambda. So if we have a Reissner-Nordstrom or a Kerr black hole with a non-zero angular momentum, then that solution can be smoothly extended across a horizon inside the black hole. So here's the usual Penrose diagram for a Reissner-Nordstrom solution. So this is the region outside the black hole interior, white hole, and the other asymptotically flat region. And so this horizon inside the black hole is this blue line here. And so you can extend across that blue horizon into a region to its future, which I've just denoted schematically by this region bounded by the orange dots here. But the important thing for this talk is that there are infinitely many ways of doing this. So there are infinitely many ways of smoothly extending the Reissner-Nordstrom or the Kerr solution across the Cauchy horizon, across this horizon, which are consistent with the equations of motion. And so that means that if you have initial data prescribed on a surface like this surface sigma here, which goes from one spatial infinity to the other spatial infinity, then if that initial data is exactly Reissner-Nordstrom, say, then the resulting solution will be exactly Reissner-Nordstrom all the way up to this inner horizon. But once you go beyond that inner horizon, there are infinitely many things it could be. There are infinitely many ways of extending the solution. And so the initial data, even if you know it perfectly, doesn't predict what happens when you go beyond that inner horizon. So that inner horizon is referred to as a Cauchy horizon. It's a boundary of the region that you can predict in the Cauchy problem from the data prescribed on sigma. So this fact that you can extend in infinitely many ways is rather worrying from the perspective of determinism. It means that we can't predict the future, even if we know the initial conditions on sigma perfectly. Even if it's perfectly Reissner-Nordstrom, we can't say what the solution is in this region beyond the Cauchy horizon. So often the reason you don't learn about this when you first encounter the Reissner-Nordstrom or the Kerr solution is you impose extra conditions on the solution to recover uniqueness. So those extra conditions are usually either spherical symmetry or analyticity. So either of those conditions would be enough to recover uniqueness. But we really shouldn't have to do this. We shouldn't have to invoke extra conditions beyond the conditions present in our initial data. So those are not very satisfactory physically. So a final comment on this Penrose diagram is I've drawn the diagram here for a two-ended initial data surface. If we were interested in a black hole formed by gravitational collapse, then you can just cover up part of this diagram with a collapsing star, for example, and then only the part of the Cauchy horizon at early time, so this section here emanating from future time like infinity, is physically relevant. So mostly we're going to focus on the part of the Cauchy horizon down here. So as I said, this is a worrying situation from the point of view of determinism. So this was first discussed by Roger Penrose, who pointed out that maybe there's a way out here, which is perhaps this behavior is unstable. In other words, the existence of a Cauchy horizon only happens for very special, infinitely fine-tuned initial data. And in fact, there's a heuristic reason to expect the Cauchy horizon to be unstable, which many of you will have seen before, which is that perturbations entering the black hole from outside experience an infinite blue shift at this Cauchy horizon. So here's the usual picture of this. So we have, here I've just shown, this is the black hole exterior, this is the black hole interior. We have two observers, Alice and Bob. Alice is immortal, she lives forever, so her world line ends at future time-like infinity here. Bob is quite adventurous and he's jumped into the black hole and he wants to find out what happens at the Cauchy horizon. And Alice is sending signals to Bob. So every second Alice sends a radio signal to Bob. These are these purple lines here. So Bob is receiving them as he approaches the Cauchy horizon. To get into the Cauchy horizon just takes finite proper time for Bob. And as you can see, as he approaches the Cauchy horizon, the signals from Alice get closer and closer together, so that the time between them tends to zero as Bob approaches the Cauchy horizon, and he receives infinitely many signals at the instant that he crosses the Cauchy horizon. So this means that the frequency of the signals as measured by Bob is diverging at the Cauchy horizon, and so there's an infinite blue shift there. So the idea is that if instead of considering signals from an observer, we considered small perturbations of the exterior geometry, then those small perturbations will suffer the same kind of infinite blue shift near the Cauchy horizon in the interior. And so they'll have a large local energy, which will cause a large gravitational back reaction, and maybe that will have the effect of destroying the Cauchy horizon and replacing it by a singularity. So that was Penrose's idea. And you can see what's relevant is the late time behavior of perturbations in the interior, because those are the ones which most directly influence the behavior at the Cauchy horizon in the interior. So if this were true, then this may be a way of rescuing determinism. It would mean that Cauchy horizons only exist for exactly Reissner-Nordstrom or exactly Kerr initial data, but if you perturb it, then the resulting solution would not have a Cauchy horizon. So here's a more formal version of the conjecture. So we consider complete asymptotically flat initial data for the Einstein-Maxwell equations. Then generically, in other words, for generic initial data, the resulting solution cannot be extended across a Cauchy horizon. And so if this is correct, this would be quite satisfying, because it's a way of restoring predictability or determinism without invoking extra physics, such as quantum effects. You'd be solving the issue entirely within the context that it first arose, namely classical general relativity. So is this conjecture true? So there's over the decades since Penrose proposed this conjecture, evidence has been accumulating in favor of it. So let's start by looking at linear perturbations of Reissner-Nordstrom black holes. So these could be massless scalar field perturbations, or they could be linearized gravito-electromagnetic perturbations. So these are coupled together. So for simplicity, let's just focus on the massless scalar in this talk. And let's imagine, so we introduce some initial data for our scalar field, which is compactly supported on our surface sigma. Going back to my diagram, sigma is this initial surface here. So we introduce a compactly supported scalar field on sigma in the Reissner-Nordstrom geometry. So how does the resulting solution for the scalar field behave? Well, outside the black hole, it's well known that solutions exhibit power law decay in these asymptotically flat black hole spacetimes. So these are called late time tails, and they arise from the scalar field scattering off the curvature of the spacetime. And this power law decay is slow enough to be effective in triggering this blue shift instability that I just described at the Cauchy horizon, with the result that the gradient of the scalar field diverges at the Cauchy horizon. And this means that the energy density measured by Bob, or by an observer who crosses the Cauchy horizon, is divergent. And so all of this is in agreement with the picture I just described. And we would expect, when we go beyond the linear scalar field and include the back reaction, that this is going to cause a large back reaction on the metric. So in the 1990s, people went beyond just looking at linear perturbations and studied a nonlinear model. So Poisson and Israel introduced a model, again, for spherically symmetric perturbations of Reissner-Nordstrom, in which they introduced a kind of a toy model for the matter which is doing the perturbing. This is called null dust. It's what the name suggests. It's null and it's dust-like. So this is matter that moves along null geodesics. And what they showed is that in this model, they could show that back reaction causes a certain invariant in spherical symmetry called the Hawking mass to diverge at the Cauchy horizon. And it does so in a way which is exponential as a function of an advanced time coordinate. And so that exponential dependence caused them to call it mass inflation. But this implies that curvature scalars, such as the Kretschmann invariant, also diverge at the Cauchy horizon. And so in this simple model, the nonlinear model, one can see that back reaction causes the Cauchy horizon to become singular, in agreement with the conjecture. However, there was something quite surprising that came out of this model, is that it turns out that even though the curvature diverges at the Cauchy horizon, the metric can still be continuously extended across a Cauchy horizon, which means in particular we can still define a Cauchy horizon. So there still exists a continuous extension of the metric across a Cauchy horizon, but now the curvature diverges at that Cauchy horizon. But in particular, this means that the singularity that forms inside the black hole is null, at least at early times. So down here, the singularity would just live along this blue line. And that was a bit surprising, because Penrose's original picture was that strong cosmic censorship would cause, well, the singularity inside the black hole would be space-like, as for the Schwarzschild black hole. That turns out not to be true. At early times, at least, the singularity that forms when you perturb the black hole is null. Okay, so more recently, mathematicians have been studying this using rigorous methods. And so the model they focused on is the Einstein-Maxwell equations coupled to a massless uncharged scalar field in spherical symmetry. So we introduced the scalar field here to evade Birkhoff's theorem, so that we can still have some dynamics in spherical symmetry. And the idea is that this is a fully nonlinear model. We're considering nonlinear perturbations, small nonlinear perturbations of Reissner-Nordstrom by this scalar field phi. As before, we can take compactly supported initial data for this scalar field on this two-ended initial surface. Then what's been proved by de Fermos is that the resulting nonlinear solution can be continuously and globally extended across a Cauchy horizon. More recently, it's been proved by Luke and O that this extension generically is not C2 at the Cauchy horizon, so the curvature diverges there. But what this means is that in this model where we perturb a two-ended a black hole with two asymptotic regions, the picture we get is exactly like this, where we can extend continuously across this Cauchy horizon, and the curvature blows up on that Cauchy horizon. So it's an example of where the resulting space-time has a singularity which is globally null. It's space-like nowhere. So that again was quite surprising. So that's the picture for nonlinear perturbations of Reissner-Nordstrom in spherical symmetry. So this is when we look at perturbations on this two-ended initial surface sigma. But if we only interested in one side of sigma, if we only specify data in one asymptotically flat region, then the same kind of things are true, but they just apply to this early time portion of the Cauchy horizon, which is what I've just been describing. So you have this early time null singularity across which you can extend continuously, but not in C2. So this was for Reissner-Nordstrom, but very similar results are expected for Kerr. So a continuous extendability result for Kerr has been proved recently by de Fermos and Luke. So this sounds good. A perturbed Reissner-Nordstrom black hole can be continuously extended across the Cauchy horizon, but the extension is not in C2, and so the Cauchy horizon is a curvature singularity, which all sounds like it's in agreement with the conjecture. And so we might say that's great, determinism is restored. This curvature singularity obviously is the end of space-time. We shouldn't really go beyond that. However, it's not quite so simple. And this was realized even in the Poisson-Israel model, when Ori considered an observer who approaches this perturbed Cauchy horizon where we have this curvature singularity. So because of the singularity, tidal forces diverge at this Cauchy horizon. But from the point of view of the observer, it's not the divergence in tidal forces that's relevant. What's relevant to the observer is the cumulative effect of those tidal forces. And it turns out that this divergence in the tidal forces is an integrable kind of singularity. And so the total tidal distortion experienced by an observer who approaches the Cauchy horizon can actually remain bounded. And so the observer doesn't get infinitely distorted. So the question is, what happens to such an observer? So to answer this question, we need to say something about the dynamics which dictates the motion of this observer. So we need to specify what the observer is made of, give equations of motion for the matter fields that the observer is made of. And the question is, can we still make sense of these equations of motion at the Cauchy horizon? Would it still make sense to extend the observer across the Cauchy horizon? And if so, then we still have this problem with determinism, even though the Cauchy horizon is a curvature singularity. So to discuss this, we need to discuss the notion of weak solutions of equations of motion. So as we've seen, that the space-time is not C2 at the Cauchy horizon. So the question is, what is the minimal regularity we need to make sense of these equations of motion? In particular, one of the equations of motion will be the Einstein equation. So can we make sense of solutions which are less regular than C2? Well, in mathematics, of course, we know we can. There's the notion of a weak solution. And this is something that's quite physical. So, for example, shocks in a compressible perfect fluid are described by weak solutions of the Euler equations. And so if we apply this to the Einstein equation, then it turns out that the appropriate notion of a weak solution is that requires that the Christodoulou symbols should be locally square integrable in some chart for the notion of a weak solution to make sense. So this motivates Christodoulou's formulation of strong cosmic censorship. So he says that generically it should, although it might be possible to extend in C0, the question is whether it's possible to extend across the Cauchy horizon as a weak solution. So his version of the conjecture says that generically it is not possible to extend across the Cauchy horizon with locally square integrable Christodoulou symbols. In other words, it's not possible to extend across a Cauchy horizon consistently with the equations of motion, even interpreted in a weak sense. So if this is correct, then you can't extend beyond the Cauchy horizon in a way that the equations of motion are satisfied. And so determinism is restored.
Harvey, question?
Yes.
So, of course, this fact that you can still extend the metric continuously, is this not a little worrisome from your perspective?
No, because I mean, if I can't make sense of the equations of motion, then that doesn't bother me too much. I mean, my theory is breaking down in any sense because the equations of motion don't make sense. I think that's the way I look at that. Whereas, so I think this Christodoulou formulation is very physical because in the sense it's asking, can we satisfy equations of motion? So does the theory still make sense at the Cauchy horizon? Okay, so this version of the conjecture is believed to be true when lambda is equal to 0. So to summarize, we can distinguish different versions of strong cosmic censorship by the level of smoothness that we require at the Cauchy horizon. So in order of decreasing strength, the strongest version of the conjecture would say that generically there is no continuous extension across the Cauchy horizon. The next strongest version would be this Christodoulou version, which I've just explained, which would say generically there's no extension with square integrable Christodoulou symbols. And then weaker than that would be the C2 version, which would say generically there is no C2 extension. And so the situation is that for Einstein-Maxwell theory with a massless scalar field, with vanishing cosmological constant, we know that the C0 version, the strongest version, is false. So you can extend continuously. The Christodoulou version is believed to be true, and the C2 version is true. It's been proved in spherical symmetry. Okay, so that's my summary for 0 lambda. Maybe if there are any other questions about that, I'd be happy to answer them.
There are no questions in the chat at the moment.
No? Okay. So let's move on to non-zero lambda, which is the recent work. So I'm going to discuss first the case of positive lambda. With positive lambda, there's a new ingredient that comes in, which is now we have a cosmological horizon. So this is the Penrose diagram for Reissner-Nordstrom-de Sitter. So this is the region outside the black hole. So this is the event horizon of the black hole. And now you see we've got this new horizon in orange, which is a future and a past cosmological horizon. So if you're in this region 1, if you cross through the cosmological horizon, you enter this region here, and this contains the space-like de Sitter infinity. So over here you have another region and another cosmological horizon, and this diagram can be repeated indefinitely to the left and the right. Up here is the black hole region, down here is the white hole region. And a Reissner-Nordstrom or a Kerr-de Sitter black hole is very similar to the case for lambda equal to 0 in the sense that you still have this Cauchy horizon in blue inside the black hole, beyond which you can extend the solution smoothly as a solution of the equations of motion in infinitely many different ways. So let's just rerun our heuristic argument for why the Cauchy horizon should be unstable in this new setting with the cosmological horizon. So here I've drawn Alice and Bob again. So here I've drawn Alice crossing the Cauchy horizon, sorry, crossing the cosmological horizon, which you would do in finite proper time. But I could also draw Alice hanging around forever outside the black hole and not crossing the cosmological horizon, in which case her world line would go up here. Doesn't really matter which case I consider. The point is that the signals that Alice is sending to Bob at late time, you can see they're now having to climb out of a potential well, which is associated with this other horizon, the cosmological horizon, which is associated with the exponential expansion of space-time caused by the, or space caused by the positive cosmological constant. So this exponential expansion is redshifting everything. And so the signals entering the black hole at late time have already undergone a very large redshift before they reach the Cauchy horizon, where they suffer this competing blue shift that I discussed earlier. So now we've got a blue shift and a red shift, and so it's not clear which effect is going to win. Does the blue shift at the Cauchy horizon beat the red shift coming from the exponential expansion out here, or does the exponential expansion out here dilute everything, dilute all perturbations to such an extent that there's not enough left to trigger the blue shift instability at the Cauchy horizon? So it's not clear a priori who will win. So this was first discussed some time ago, 30 years ago, by Ian Moss and his student Felicity Meller. So they discussed Reissner-Nordstrom-de Sitter. Again, they looked at linear perturbations of Reissner-Nordstrom-de Sitter, and they argued that late time decay of linear perturbations outside the black hole is determined by quasi-normal modes of the black hole. So just a reminder, a quasi-normal mode is a solution with time dependence e to the minus I omega t, which is smooth on the future event horizon and the future cosmological horizon, which means that omega turns out to be complex with negative imaginary parts. So these are solutions which decay exponentially in time whilst oscillating. So they describe damped oscillations of the black hole. So in de Sitter space, the slowest decaying quasi-normal mode actually fixes the decay of generic linear perturbations. And so if we look at the rate of decay of that slowest quasi-normal mode, we define the spectral gap alpha to be the minimum value of minus the imaginary part of omega over all quasi-normal modes. And then one expects that generic perturbations will decay exponentially in time as e to the minus alpha t for a de Sitter black hole. And so this is in contrast with what happens for lambda equals 0, the asymptotically flat case, where perturbations exhibit power law decay. Here in de Sitter, it's much faster. At late times, we have exponential decay of linear perturbations. So the question is this decay, this potentially rapid decay, slow enough to trigger the blue shift instability of the Cauchy horizon?
I'm sorry.
So to analyze that, one can introduce cross-scale-like coordinates near the Cauchy horizon, so that the Cauchy horizon is at v equal to 0, with the black hole interior in the region of negative v. Question.
It's not a question. I mean, I think one of the participants has a question, Maddie.
Someone raised their hand but lowered it again. So perhaps if there's a question, raise your hand again so we can.
Yeah.
Sorry, I couldn't unmute myself. I was just going to ask whether alpha depends on the cosmological constant.
Yes, alpha depends on the black hole parameters. So it depends on the
and also the mass, or.
Yeah, it's a function of the background space-time, so it depends on the black hole mass, charge, and the cosmological constant. Yeah.
Thanks.
So it's basically the decay rate of the slowest decaying quasi-normal mode.
Nice.
Good. What Meller and Moss showed is that near the Cauchy horizon, when you propagate generic linear perturbations into the black hole interior, you find that near the Cauchy horizon, they behave as minus v to the power beta. So v vanishes at the Cauchy horizon, where beta here is a constant given by the spectral gap alpha divided by kappa minus, where kappa minus is of the surface gravity of the Cauchy horizon, which is positive in my conventions. And so from this formula here, you can see that if beta is less than 1, then the gradient of perturbations will blow up at the Cauchy horizon, which would be in agreement with strong cosmic censorship. And as you can see, that depends on alpha, which is the rate of decay of perturbations outside the black hole. So the perturbations have to decay sufficiently slowly on the scale set by kappa minus. So to determine beta, you have to calculate alpha. To calculate alpha, you have to calculate quasi-normal modes of these black holes, which requires numerics. So Meller and Moss showed that numerically, most Reissner-Nordstrom-de Sitter black holes do have beta less than 1. And that would mean that the gradient of the scalar field will blow up at the Cauchy horizon, and then back reaction would cause curvature to blow up in agreement with the C2 version of strong cosmic censorship. However, they also claimed that if you look at near-extremal Reissner-Nordstrom black holes, then in this case you can have beta greater than 1. And this would, if that's correct, that would entail a violation of the C2 version of strong cosmic censorship. However, we have to say that calculating these quasi-normal modes is actually quite tricky. So to determine alpha, you have to really make sure you've found the slowest decaying quasi-normal modes. And techniques for calculating quasi-normal modes back in 1990 were not as good as they are now. So it's not, so the numerics here were perhaps not as convincing as they could have been. But nevertheless, they had this claim. And this was then discussed throughout the 1990s until Ian Moss and some other collaborators, Patrick Brady and Rob Myers, wrote a paper in 1998, which concluded that looking at quasi-normal modes is actually not enough for discussing strong cosmic censorship, and that the C2 version of strong cosmic censorship is actually respected by Reissner-Nordstrom-de Sitter. Okay, so that essentially ended the story in the 1990s. They concluded that in fact strong cosmic censorship was true because you can't just look at quasi-normal modes. Unfortunately, it turns out that there's a problem with this paper, this conclusion, or the argument in this paper. So I won't describe the argument because it turns out not to be correct. So more recently, mathematicians have returned to this problem. And for smooth initial perturbations, what Hintz and Vashi have shown is that the behavior of linear perturbations at the Cauchy horizon is, in fact, determined by quasi-normal modes, as originally claimed by Meller and Moss. So the original Meller-Moss analysis actually was correct, and it's backed up by this rigorous work of Hintz and Vashi. So in fact, the earlier claim still stands. that it's this value of beta which determines whether or not strong cosmic censorship is respected, and it does just reduce to looking at quasi-normal modes. So if the nonlinearities behave as expected, then the Christodoulou version of strong cosmic censorship will be respected if beta is less than 1/2, and the C2 version will be respected if beta is less than 1. So the question now is, what is the value of beta? And to calculate beta, one needs to determine quasi-normal modes of these black holes. So this was discussed by Cardoso and collaborators at the end of 2017, and they did a careful numerical study of massless scalar field quasi-normal modes for Reissner-Nordstrom-de Sitter. So as I said, you have to calculate the slowest decaying quasi-normal modes to determine beta. So just a reminder, beta is the ratio of the decay rate of the slowest decaying quasi-normal mode to the surface gravity of the Cauchy horizon. And what Cardoso and collaborators found is that near-extremal Reissner-Nordstrom black holes have beta between 1/2 and 1. And that means that they respect the C2 version of strong cosmic censorship because beta is less than 1, but they violate this Christodoulou version of strong cosmic censorship. In other words, this result indicates that you can extend across the Cauchy horizon consistently with equations of motion. And so we have a problem. So this was for linear perturbations. There's no reason to expect nonlinearities would cause a problem, and indeed people have done numerical simulations in spherical symmetry of the nonlinear problem and confirmed that is indeed the case. So this conclusion survives, including nonlinearities. So that now brings me to what we did.
Harvey, question.
Yes.
So this lunar work, it's a spherical a scalar field or what is the field here?
Yeah, it's just a scalar field in Reissner-Nordstrom-de Sitter. Spherical symmetry.
Uncharged. Mm-hmm.
Uncharged.
Okay,
yeah.
Thanks.
Okay, so now come to our work. So what we did was to get rid of the scalar field, and we discussed perhaps the more physical problem of gravitational and electromagnetic perturbations of Reissner-Nordstrom-de Sitter, which are coupled together. And so we determined quasi-normal modes for these fields. And what we found was quite surprising, is that we found that near-extremal Reissner-Nordstrom black holes always have beta bigger than 2. So that means that if we're looking at pure Einstein-Maxwell theory, not only is the Christodoulou version of strong cosmic censorship violated, but so is the C2 version. So that this result indicates that the curvature won't blow up at the Cauchy horizon. The fields can be extended in C2 across the Cauchy horizon if we're sufficiently near-extremal. And in fact, it's worse than that. So you can show that generic perturbations are CR at the Cauchy horizon, where the value of R can be made arbitrarily large by taking the black hole to be sufficiently near-extremal and sufficiently large in units of lambda, the cosmological constant. Okay, so you can make perturbations as smooth as you like by considering a large near-extremal black hole. And so this shows that strong cosmic censorship is very badly violated in Einstein-Maxwell theory with positive lambda. So essentially any version of strong cosmic censorship you can think of is going to be violated by these black holes. Well, when I say any version you can think of, I mean for any degree of smoothness, for any value of R. So that's a pretty bad violation of strong cosmic censorship. That was for Reissner-Nordstrom-de Sitter, which isn't terribly physical. What is physical is positive lambda, which of course is our universe. What's not so physical is near-extremal Reissner-Nordstrom-de Sitter, because highly charged black holes don't exist in nature. But of course, Reissner-Nordstrom is often regarded as a toy model for Kerr. And so the question now is, does this violation of strong cosmic censorship for Reissner-Nordstrom-de Sitter indicate that there's going to be a problem for the very physical case of Kerr-de Sitter? So we studied this. In fact, this is the first thing we did in our first paper. We looked at quasi-normal modes of Kerr-de Sitter, and you can do this analytically by considering quasi-normal modes with large angular frequency, so modes proportional to e to the im phi, where phi is the usual angular coordinate in the Kerr solution, and m we take to be very large. So in this limit, you can use geometric optics to calculate quasi-normal modes, and the problem reduces to just looking at properties of null geodesics in these spacetimes. So the null geodesics in questions are associated with the photon sphere of the black hole. So this consists of null geodesics which remain forever at fixed r. So these are unstable geodesics, of course. When you perturb them, they either fall into the black hole or cross the cosmological horizon. But in geometric optics, the decay rate when you perturb one of these geodesics fixes the imaginary part of the associated quasi-normal mode. So by looking at these geodesics, we can get an upper bound on beta. Because we have an upper bound on the decay rate of perturbations from looking at these geodesics. And the result is that beta is less than a half, with beta tending to a half in the limit that the black hole becomes extremal. And remember, a half was the critical value for Christodoulou's version of strong cosmic censorship. And so this result shows that for Kerr-de Sitter, strong cosmic censorship is respected. Christodoulou's version of strong cosmic censorship is respected. So this physical version of strong cosmic censorship is respected for Kerr-de Sitter. So what does this mean in summary is that when lambda is positive, this physical Christodoulou version of strong cosmic censorship is respected in pure Einstein gravity, but it's violated in Einstein-Maxwell theory. So it's respected for Kerr-de Sitter, but violated by Reissner-Nordstrom-de Sitter. And I should have said the perturbations we were talking about here are gravitational perturbations, linear gravitational perturbations. They could have been scalar field perturbations, but you can also do the gravitational case. Okay, so that's a little bit surprising. So that was positive lambda. Let me now say something about negative lambda. So here things are rather different. Again, it turns out that perturbations outside the black hole the decay of linear perturbations can be understood by looking at quasi-normal modes, as for the case of positive lambda. And by looking at quasi-normal modes in 4 dimensions, you can see that the perturbations of an anti-de Sitter black hole decay very slowly. This is because of a phenomenon called stable trapping, which means that null geodesics can orbit the black hole at large distance in a stable.
Harvey, question.
Yes.
So is there an equivalent of the Hinz-Fasci theorem for lambda positive? And when you take lambda negative?
You mean the one relating the decay
The
outside?
linear decay, right? Yeah.
I don't think that's been proved rigorously. I'm tempted to say no.
Okay, thanks.
Well, actually, I don't think it's so relevant. As I'm going to explain why it's not so relevant now. So maybe that will make it a bit clearer. So I will explain what the relevant work is. So the point is that if you look at quasi-normal modes of very high frequency, then the decay rate of quasi-normal modes of very high frequency tends to 0. As you take when I say frequency, I mean angular wave number. As you take the angular wave number to infinity, the decay rate of quasi-normal modes tends to 0, which means that perturbations of an anti-de Sitter black hole decay very slowly. In other words, the spectral gap is 0. This means that generic perturbations of an anti-de Sitter black hole actually decay as an inverse logarithm of the time coordinate, which is even more slowly than the power law decay you get in the asymptotically flat case. So since the decay is even slower than in the asymptotically flat case, you might expect this to lead to an even stronger version of the instability of the Cauchy horizon than is present in the asymptotically flat case. And so it's expected, therefore, that the Christodoulou version of strong cosmic censorship is even more likely to be true for negative lambda than it is for positive lambda, just because perturbations of the black hole decay so slowly. So in fact, you might even wonder whether the strongest version of strong cosmic censorship, that the C0 version, maybe that's true for these anti-de Sitter black holes. So this has been investigated for the case of a linear scalar field with conformal coupling by Christoph Kähler. And in fact, he's proved that the C0 version of strong cosmic censorship is actually false for Reissner-Nordstrom-ADS, just as it's false for Reissner-Nordstrom with lambda equal to 0. So this effect, it turns out, doesn't strengthen the instability to an extent that you recover the C0 version of strong cosmic censorship. So in other words, you can still extend continuously across the Cauchy horizon of a perturbed Reissner-Nordstrom-ADS black hole. However, if you look at Kerr-ADS, then things are much more subtle. So here it turns out that the C0 version of strong cosmic censorship is respected. In other words, you get a blow up of the scalar field at the Cauchy horizon. If the black hole parameters belong to a set which is what Kähler calls bare generic, but Lebesgue non-generic. So roughly speaking, this is a bit like the rational numbers within the real numbers. So if the black hole, so it's a set that's dense but of 0 measure. So if the black hole parameters belong to this set, then the scalar field will diverge at the Cauchy horizon. You cannot extend in C0. But if they do not belong to this set, in other words, if they belong to the set with non-zero measure, then things are just as for Reissner-Nordstrom-ADS, and you can extend in C0. So it turns out that whether or not you think the C0 version is respected depends on which notion of genericity you want to use here. So this is rather surprising. It's conjectured that by Kähler this result will be sharp in the linear theory. Okay, so this is a surprising result for negative lambda. But I should emphasize that the Christodoulou version, the physical version of the conjecture, is expected to be satisfied for these black holes. One of the interesting things you can do with negative lambda is that you can construct black holes in lower dimensions. So in three-dimensional space-time with negative lambda, there's the BTZ black hole, which is basically Kerr-ADS in 2+1 dimensions. Okay, so this is a black hole solution which is locally but not globally isometric to anti-de Sitter space, and it plays an important role in the ADS CFT correspondence. So in our final paper on strong cosmic censorship, we studied perturbations of this black hole and asked how they behave. We looked at perturbations of various types. So we looked at scalar field perturbations, but there are more exotic things you could look at, like massive vector fields or massive spin-2 fields. They all behave very similarly. The novel thing about the BTZ black hole is this trapping effect, which causes the slow decay in 4 dimensions, is not present. And that means that for BTZ, linear perturbations decay exponentially fast, as in Reissner-Nordstrom-de Sitter. And so the criterion for the Christodoulou version of strong cosmic censorship to be respected is exactly the same. It's beta less than a half, the same criterion as we had for positive lambda. So the nice thing about this solution is that you can do everything analytically. You can solve all the equations using hypergeometric functions. The quasi-normal modes, their frequencies are all known explicitly. And so what we found is that for any type of perturbing field, the situation is very similar to Reissner-Nordstrom-de Sitter. So we can make beta as large as we like by taking the black hole close enough to extremality. Okay, so again, we have a violation of strong cosmic censorship, where you can make the behavior at the Cauchy horizon as smooth as you like by considering a sufficiently sufficiently close to extremality black hole. So very similar to Reissner-Nordstrom-de Sitter. In fact, Franz Pretorius and his collaborator Pandya have done numerical simulations of collapse in 2+1 dimensions, and their simulations are in agreement with what we found in the linear study, and they support the idea that nonlinearity isn't going to change any of this. So we have a bad violation of strong cosmic censorship for the BTZ black hole. So to summarize, we've seen the Christodoulou version of strong cosmic censorship is violated by near-extremal Reissner-Nordstrom-de Sitter and also by BTZ. So the question is there any way now of rescuing strong cosmic censorship? And so I'm going to discuss two ways of doing this. One is classical and one is quantum. So let's start with the classical. And let me emphasize something I've not emphasized so far, which is that in all of this story so far, when I've been discussing perturbations, I've been considering initial data for the perturbation, which is smooth. So all of our perturbations arise from smooth initial data. That's what people have always done when studying strong cosmic censorship. In particular, that's what people do for lambda equal to 0. So what de Fermos and Schlappentock-Rothman have suggested is that a way out, or a way of rescuing strong cosmic censorship, is to enlarge the class of admissible initial data by allowing it to be rough, so not smooth. And so if your initial data is not smooth, then the late time behavior is no longer dictated by the quasi-normal modes. And what you can show is that the smoothness of the solution in the sense of Sobolev spaces generically gets worse at the Cauchy horizon. So you can do this quite explicitly by just writing down some solutions of definite frequency and looking at how they behave. So in particular, if you have some notion of what the minimal acceptable level of smoothness is, and you start off with generic initial data with that smoothness, then generically at the Cauchy horizon, your solution will not have that minimal acceptable level of smoothness. So if you, so as a concrete example, if you insist that your initial perturbation, let's say it's a scalar field, has to live in the Sobolev space H1, then generically it will not be an H1 at the Cauchy horizon. Okay, it will be less smooth. So that in that sense, you can rescue strong cosmic censorship by enlarging the class of initial data to include this rough data. And essentially the only important thing you need in this argument is an inequality satisfied by the surface gravity. So it turns out that the Reissner-Nordstrom-de Sitter black hole satisfies this inequality between the surface gravities of the Cauchy horizon and the event horizon. And this is enough to guarantee this behavior. Turns out this inequality is also satisfied by Kerr-de Sitter, and it's also satisfied by the BTZ black hole. So this argument also works as a way of rescuing strong cosmic censorship for BTZ if you're willing to consider rough initial data. It's surprising that this inequality always holds. There must be some reason for it. I don't know what that reason is. Why this inequality seems to hold for all interesting black holes with Cauchy horizons. So it would be interesting if there was some deep reason for it. Okay, so that's one way of rescuing strong cosmic censorship by considering rough initial data. The final thing I'm going to talk about is a different way of rescuing strong cosmic censorship, which is to turn to quantum effects. So the question is, if we look at Reissner-Nordstrom-de Sitter or BTZ, can quantum effects help save strong cosmic censorship? And the particular quantum effect I'm going to talk about is vacuum polarization, which is the phenomenon that when you look at quantum fields in curved space-time, even if you put them in some symmetrical state that you might want to regard as a ground state, you'll find that the expectation value of the energy momentum tensor is non-zero. Okay, so when we now take account of gravitational back reaction, which we can do through the semi-classical Einstein equation by putting this expectation value on the right-hand side, then vacuum polarization will affect the space-time geometry. So a long time ago, it was shown in a two-dimensional toy model of a black hole with a Cauchy horizon that this expectation value will diverge at a Cauchy horizon. And so maybe this is a way of rescuing strong cosmic censorship. Okay, so this was just for a two-dimensional toy model. So the question is, could this rescue strong cosmic censorship? Is there a similar divergence for BTZ or for Reissner-Nordstrom-de Sitter? And is the divergence strong enough? So it's not enough that it diverges, it has to diverge in a sufficiently strong way that you can't extend across the Cauchy horizon consistently with the equations of motion. So that's what we want to discuss. So the first investigation, this was actually something we discussed in our paper on BTZ. So for BTZ, you can calculate this explicitly at least for the most symmetrical quantum state of a quantum scalar field in the BTZ geometry, so the so-called Hartle-Hawking state. And we showed that in fact, if you have a near-extremal black hole, this thing does not diverge at the Cauchy horizon. So one can prove that the vacuum polarization, that the expectation value of the stress tensor extends continuously to the Cauchy horizon of a black hole with beta bigger than 1. And remember, beta became arbitrarily large for a sufficiently near-extremal black hole. So for a near-extreme, so if you have a black hole far from extremality, beta will diverge at the Cauchy horizon, but near extremality, beta remains finite on the Cauchy horizon. And so
question?
Yes.
Is there a feeling that this expectation value will might blow up in other states, or is it obvious? Is it clear? Is it?
I'm going to discuss that in a minute. So,
okay.
Yeah, our calculation was just for Hartle-Hawking. So at this stage, you're right. You're correct. We could imagine that maybe there's some other state which would give us something different. But in fact, that's not the case. So anyway, for BTZ, this doesn't help. What about Reissner-Nordstrom-de Sitter? Well, here the calculation is much harder because the space-time is more complicated. But nevertheless, recent work of Hollands-Wald and Zahn has determined the behavior of the expected value of TAB at the Cauchy horizon for a scalar field in a generic quantum state. Okay, and their result is that the stress tensor diverges at the Cauchy horizon proportional to v to the -2, where v is the Kruskal-like coordinate which vanishes on the Cauchy horizon. So their result is that generically you do have this divergence at the Cauchy horizon for Reissner-Nordstrom-de Sitter, and they showed that this c here is actually state independent. So this constant here depends just on the parameters of the black hole. Okay, so either you get a divergence for all quantum states or for none. And so they showed for Reissner-Nordstrom-de Sitter, this constant c is generically non-zero. Furthermore, this divergence is quite strong, v to the -2. It's strong enough to rescue the Christodoulou formulation of strong cosmic censorship for Reissner-Nordstrom-de Sitter. And so this shows that for Reissner-Nordstrom-de Sitter, quantum fields do actually give us an effect which is strong enough to rescue strong cosmic censorship. So you might ask, how does this fit in with our earlier BTZ result? Well, it turns out that BTZ is special because this constant c just always vanishes for BTZ. It just turns out that it's always 0. So we don't get this divergence. However, there is possibly still a way of using quantum effects to rescue strong cosmic censorship here, which is to say that, well, for BTZ, this expectation value is non-zero. It doesn't diverge if we're near extremality, but it's still non-zero. So there's still going to be some back reaction on the space-time geometry when we plug into the semi-classical Einstein equation. And when we consider now this deformed geometry, in the deformed geometry, this constant c, there's no reason now why it will still vanish. And so it's now plausible that if we now went to second order in h-bar in some sense, then second order quantum effects will rescue strong cosmic censorship. So this argument was made by Roberto Emperan and his student. Okay, so we would, by the first order quantum effects would destroy the special symmetry of BTZ, which gave us c equal to 0. And so when we go to second order, the expectation is that c will be non-zero and we'll see this divergence. Okay, so this is just expectation. These calculations would be incredibly difficult to actually do to confirm this, but it seems like a plausible argument. Okay, so coming to the end of my talk, let me summarize. So strong cosmic censorship says basically that physics should be predictable from initial data. As I've explained, it's very likely to be true for four-dimensional black holes with lambda 0 or negative. I've explained how it's true for four-dimensional pure Einstein gravity with positive lambda, in other words, for Kerr-de Sitter black holes. But we've seen that it's badly violated in a pure Einstein-Maxwell theory with positive lambda, in other words, Reissner-Nordstrom-de Sitter, and also in 3 dimensions with negative lambda by the BTZ black hole. So then to rescue strong cosmic censorship, if you want to rescue it, you can do it classically by enlarging the class of permissible initial data to include rough initial data. And as I've just explained, quantum field theory effects can also save strong cosmic censorship. So thank you for listening.
Thank you very much, Harvey, thank you for this beautiful talk and for presenting us to your results on this. So we're ready to take questions.
Piotr, may I ask a question? Can you hear me?
Go ahead, Jacek.
So my question is basic. It's related to singularity of curvature on some hypersurface. For instance, Cauchy horizon. So the metric is continuous, as I understand. So we have space-times on both sides of this hypersurface. Mm-hmm. So in general, in such setup, there exists some shell on this hypersurface. So how it is here? So which means that the Ricci is vanishing, or
there's no kind
of Einstein equations on this hypersurface.
So the Einstein equation is still satisfying. It's kind of like I guess it's the Reall part of the curvature which is diverging there.
Only Reall, yes?
Yeah, so the Einstein equations are still satisfied, so they're still determining Ricci. But yeah, it's the Reall type divergence that's happening there. Well, I guess Ricci's diverging as well. No, so maybe I'm saying that slightly wrong. So the scale, if you look at Einstein gravity with the scalar field, so the model that de Fermos studied, so the scalar field is diverging at the Cauchy horizon. Sorry, its gradient is diverging at the Cauchy horizon. So the Ricci is also diverging at the Cauchy horizon, but it's doing it in a way which still satisfies. Sorry, no, it doesn't still. No, I'm saying this completely wrong. Okay, no, so yeah. The point is that the expectation is Ricci is diverging at the Cauchy horizon, and the energy momentum tensor is diverging at the Cauchy horizon. The expectation value, the expectation is that they are doing this in a way which is sufficiently strong that you cannot make sense of the Einstein equations at the Cauchy horizon. Okay, that's what the Christodoulou version is saying.
Even in distributional sense, yes?
Yes, correct.
Okay, thanks. Mm-hmm.
We have a question from Annegret Bircher. Annegret?
Yep.
Hi, Annegret.
Yeah, I just have a question that, well, does this behavior for the Einstein-Maxwell maybe also suggest that this is not the right electromagnetic theory, and maybe it would hold for another one, a nonlinear one or something like that?
I'm not sure that nonlinear. Well, okay. So if you make it nonlinear, I suspect what will happen is that the background solution, so the analog of Reissner-Nordstrom-de Sitter, may no longer have a Cauchy horizon. I'm not sure about that, but by considering a different theory, then the black hole solution itself would change, and so it may no longer have a Cauchy horizon. Then of course you don't have a problem even at zeroth order.
There's a question from the chat by Andrzej Roswarowski. Can you just I'll read it and then I give my interpretation. So the question is, could you remind why polynomial decay of perturbations is not present for lambda larger than 0? You said that there is purely exponential decay. So
yeah,
probably if you can comment on this rather than remind, because it's not an easy answer, right?
Yeah, it's not. I mean, it's not terribly easy to explain simply, but it's kind of related, I think, to you can see it sort of in the analytic properties of mode functions in asymptotically flat spaces. So from the behavior near infinity, you can see that the mode functions, I think, have a branch point at omega equal to 0. And so this branch point is ultimately what gives you this polynomial decay. But if you have positive lambda or negative lambda, then the behavior at infinity is different. Positive lambda, you don't have to go to infinity because you have a cosmological horizon. So you no longer have this branch point, and so you no longer get this this polynomial decay. So that will be one way of thinking about it.
Thanks. We have a question from the audience, Ali Serai. Please unmute yourself.
Yes, thank you. So I wanted to ask, is there a physical intuition why the situation is so different in Einstein-Maxwell theory?
No, I don't really have any physical intuition. It's just surprising that it happens for Reissner-Nordstrom-de Sitter, but not for Kerr-de Sitter. I mean, you could also consider, of course, Kerr-Newman-de Sitter, and there you'd see a kind of phase transition where for slowly rotating Kerr-Newman-de Sitter near extremality, it would be more like Reissner-Nordstrom-de Sitter, and for more rapidly rotating near extremal Kerr-de Sitter, it would be more like Kerr-Newman-de Sitter. It would be more like the Kerr case. But no, I don't have any intuition for why it turned out like this.
And if you replace the Maxwell field with some scalar field, I don't know if this kind of solution is known, but does the same thing will hold, or?
You mean you want to replace the Maxwell field with the scalar field in the black hole solution, or just when you do the perturbation?
Yes, so instead of considering perturbations of the Einstein-Maxwell theory, Einstein some scalar theory.
Well, so what was done first was you can look at the Reissner-Nordstrom-de Sitter solution and you can perturb it with a scalar field. Is that what you mean?
Yes. Somehow.
Yeah, okay, so that's what Cardoso and his collaborators looked at. So in that case, you see a violation of the Christodoulou version of strong cosmic censorship, but not the C2 version of strong cosmic censorship.
Mm-hmm. Thank you.
We have a question from Piotr Bizań.
Yeah, so my question is that this computation of beta is a purely linear thing. And you mentioned several times that you don't expect back reaction effect to change the conclusions. And it's not, well, as the way I see it, it's as long as, for example, these numerical simulations observe mass inflation, then it's fine. Then you rescued cosmic censorship. But if you don't observe mass inflation, I can't see how you can reach conclusions that you violated cosmic censorship, because your simulation is always in finite time. And how do you know that mass inflation won't happen for longer times of evolution?
Well, 2 points. So firstly, when we violate strong cosmic censorship, that's precisely the situation where the linear perturbations are very smooth and behaving nicely at the Cauchy horizon, which is precisely when we expect nonlinearities to be most likely to be under control. Okay, so it's precisely when we have a violation in the linear theory that we would expect the nonlinearities not to be important. And it's actually the other way around. It's when the linear theory is consistent with strong cosmic censorship. In other words, when linear perturbations are blowing up, that's the situation where we might wonder whether nonlinearities are doing something different from we might expect. So,
but if you have a real gravitational collapse, then the parameters of your background black hole change in time, right?
Course,
so
yes.
beta changes as well.
Yeah. So when you're doing a linear, if you want to study this using a numerical simulation, what you have to be careful to do is to choose your initial conditions so that the final values of the black hole parameters, in other words, the final Bondi mass and the final value of the charge, lie within the regime where the linear theory indicates that there would be a violation of strong cosmic censorship. So that's what you have to do. So this is what's been done. So by Cardoso and collaborators for the case of Reissner-Nordstrom-de Sitter in spherical symmetry with the scalar field. but also in 2+1 dimensions in the BTZ case, Franz Pretorius, as I said, has done simulations of collapse, and they've arranged that the final black hole is in this regime where we see a violation of strong cosmic censorship in the linear theory, and they're saying that this is in agreement with their nonlinear results. So nonlinearities are not changing our conclusion.
Thank you. Thank you.
Thank you very much. Next question from Lorenzo Gavassino. Please unmute yourself. Lorenzo? No? Okay.
Yes, good morning. Can you hear me? Sorry,
yes, we can hear you now.
I was having troubles. Good morning. I would like just to ask a question regarding using the scalar field. So the idea is I have some kind of other field and I will create perturbations with that. But we know that the standard model is full of possible fields. We have spinor fields, we have a lot of possibilities. We have also the gluon field that is, so isn't it conceivable that in all these population of fields, there will be some fields that anyway, when you make perturbations with them, you will destroy all this situation and you will manage to prove the cosmic censorship?
Well, first point is that the original motivation for including the scalar field, which I think goes back to Christodoulou, is that it gives a way of evading Birkhoff's theorem. So the idea is that somehow the scalar field is a proxy for the gravitational field, but we'd like to study everything in spherical symmetry, and we can't do that because of Birkhoff's theorem. So we introduced this scalar field, but the hope is that it's telling us something about what would happen when we consider gravitational perturbations in the absence of spherical symmetry. Second thing is that if we look at the standard model, then the standard model is a quantum field theory. The only fields in the standard model that really make sense classically, well, the only field is actually the Maxwell field. Everything else needs a quantum mechanical description because the associated particles are either fermionic, so you can't build macroscopic superpositions of them, or they're unstable. They don't live for very long. So it's only really if you insist on the fields belonging to the standard model, then the only one that you can really discuss classically is the Maxwell field.
Well, but for example, we know that the photon, the Maxwell theory is just the low energy of the electroweak. So for example, when one takes Reissner-Nordstrom, we already expect that it's not a complete description, or am I missing something?
No, I'm just saying that to describe the rest of the electroweak sector, the W and the Z bosons, you can't really do that classically because those particles are unstable. You have to, so if you're going to go beyond just looking at Maxwell theory, you'd have to do some kind of quantum field theory calculation rather than just some classical calculation.
Another question from Madi Godasgar. Madi?
No, sorry, I didn't have a question.
Okay. Then Yuri Teistra. We can't hear you, Yuri. Yuri, can you unmute yourself? Or good. Well, if there are no more questions, then Harvey, thanks a lot again for this. Oh, okay.
Can I just ask one question?
Lars, very good.
I mean, genericity is always a problem in these kind of considerations. And you mentioned this at one point, sort of bare genericity versus Lebesgue genericity and so on and so forth. And I mean, which of all these results that you have mentioned is the most solid from the point of view of genericity and so on? Or I have the impression that as long as you talk about some kind of symmetric situation, you're always going to have that problem. And so if you could just comment on what is the most robust result from that point of view.
Well, I think that, I mean, this thing about Baer versus Lebesgue genericity, I mean, the point is this was a surprise. This was something completely new where the interpretation would depend on what the exact notion of genericity is. So I think all previous results, it didn't really matter too much. So any sensible notion of genericity would give the same answer. So yeah, so I think it was rather surprising that turned out to be the case in the Kerr-ADS discussion.
Yeah. So because I mean so this Baer genericity versus Lebesgue genericity also comes up if you look at you know, like Bianchi cosmologies. And there's been a long-standing problem, you know, to what extent you have a silent singularity in Bianchi cosmologies. This goes back to you know, this chaotic cosmology conjecture and all that. And this has been analyzed quite recently, and the situation is extremely complicated. You can have, in some situations, you know, Baer generic behavior, or the conjecture can be satisfied Baer generically, but at the same time, you know, Lebesgue genericity can hold. So I don't even have a clear picture, but it seems to me that I found that quite interesting, that this now has come up in this situation as well.
Yeah, it's surprising because it doesn't happen for lambda equals 0. So for lambda equals 0, the notion.
It does not. Okay.
It was just that. So it's the only example I think is this Kerr-de Sitter. So yeah, it is very surprising.
Right, and I mean, I guess one point that was raised in connection with this Bianchi situation is that due to the wild nature of the sets where one behavior holds versus the other, you really cannot draw any kind of physical conclusion from that, because these sets are so intertwined, so to speak.
Yeah, so I think I agree. So in this case for Kerr-de Sitter, yeah, it's all linear, of course. So what does this mean for the nonlinear story is very unclear.
Well, so thanks again. We have normally a 2 minutes break, which let's make it 5, right? So I'm going to give the chair over to David Feynman, and I propose that we get a 5 minutes break. So let's start at 11:20.
Okay.